Okay, so now I'm on page 29 of the notes packet. We're going to list 3 facts about the remainder r obtained in the synthetic division of f of x by x minus k. So number 1, the remainder r gives the value of f of x at k. F at x equals k, I'll write it. So that is r equals f of k. Alright, number 2, if r equals 0, so if we have a remainder of 0, then we can say x minus k is a factor of f of x. And if r equals 0, so we know if something is a factor, then the ordered pair k0 is an x-intercept of the graph of f. So we are going to use synthetic division as we're performing the rational zero test. So the purpose of the rational zero test is to develop a list of potential factors, or potential zeros, I should say. So yeah, use the rational zero test to determine possible rational zeros of polynomial functions. So we're going to develop a list of potential zeros. Let's see. So our state the rational zero test. Alright, so we have a polynomial function here. I might go back to this one. And here's how we write it. We say we have our first coefficient times the highest power of the variable. So say this is x to the 5th, we'll call this a5. And then as we write our polynomial, everything is in descending order. So this would be the coefficient number 4, and this is our power, whatever the highest one is, minus 1, and then we keep going all the way down until we get to the last few. So the second to the last one is a2x2, the first one is a1, and then that's x to the first, and then we have our constant. We'll call that a0. Okay, so if we look at all of the factors, so P is all of the factors of the constant term, so the last one, and Q is all factors of the first term. So the rational zeros are all of the values of P over Q. So how do we use the rational zero test? So we can list all potential factors of our polynomial, then use synthetic division to test them, to see if we get a zero remainder. So let's just go through and do an example, and hopefully this will become much more clear. So we want to list all the possible rational zeros of this polynomial. So I'm going to be looking down here. This is P, and up here this is Q. And so all of the possible factors, or all of the possible factors of -5 are, well, it's a prime number, so the only things that go into it are 1 and 5. and they're positive and they're negative. And so then for Q, all the possible factors, again, 3 is a prime, so the only things that go into it are 1 in itself. So the potential rational zeros are all of the values of P over Q. So as I'm making a list, I could do 1 over 1, 1 over 3, 5 over 1, 5 over 3. Those are all the possible zeros of that function. So 1 over 1, 5 over 1, 1 over 3, and 5 over 3. So list some strategies that can be used to shorten the search for actual zeros. So if you are doing these problems and you're on a calculator available portion of the test, you're going to graph that function. Okay, and so if you graph the function and you're looking at it and you see that it crosses at x equals 1, then you're going to say, oh gee, 1 is probably a 0 of my function, and that's going to be the first one that you pick. Now, if you're on a non-calculator portion of the test, or if you're out driving around in your car and you just don't want to calculate and drive, then you might have to just choose some values at random and synthetically divide them and see. But otherwise, if we have our calculator, we want to use that as a tool. So this problem doesn't actually say I have to solve it out. So let's see what's next. Other tests for zeros of polynomials. Okay, so I am going to go through the upper and lower bound rules, and then I'm going to show you an example of using Descartes' rule of signs to determine how many and which type of zero there are of polynomials. So for the upper and lower bound rules, we're going to let f of x be a polynomial with real coefficients, and a positive leading coefficient. Suppose we take this polynomial, f of x, and divide it by x minus c using synthetic division. If c is greater than 0, and each number in the last row is either positive or 0, then c is an upper bound for the real zeros. Then c is an upper bound for the real zeros. And if c is less than 0, and the numbers in the last row are alternately positive and negative, and then 0 counts as either, then c is a lower bound for the real zeros of f. So explain how the upper and lower bound rules can be useful in the search for the real zeros of a polynomial function. I think basically in our last example where we had a big list, so this list isn't that huge of factors. You just have 1, 2, 3, 4, 8 different possible things you could plug in. So it's not the end of the world if you had to plug them, and there's going to be 5 potential zeros. So, but if you plugged in, say, a positive 1 and you got a positive remainder, then you could say, well, positive 1 is the highest root, and you wouldn't have to bother plugging in 5/3 or 5. So it can help limit the number of long division problems or synthetic division. That you need to do. Okay, so what I would like to do, well, we're going to have a few problems during class, but I want to do a Descartes problem. So I'm going to just call this example 9, and we're going to list the possible real zeros, and then we're going to use Descartes' rule of signs to look at how many variations in signs there are. So if f of x equals 3x to the third minus 5x squared plus 6x minus 4. So we're going to look at how many times the sign changes. So this one's positive, this is negative. Positive, negative. So we have 1, 2, 3 sign changes of f of positive x. So according to Descartes' rule of signs, the number of variations in sign, so we either have 3 positive real roots, or we have we're going to decrease that by an even number. So we either have 3 positive real roots, RR, or 3 minus 2, or 1 positive real root. Then I'm going to plug in f of negative x. So I'm going to plug it in and show the steps first. So f of negative x and then negative x cubed, it's negative 3x to the third. This is positive, so that one doesn't change. So now I look at how many sign changes there are. This is negative to negative is not a sign change, to negative is not. So we actually have 0 sign changes, so that tells me that there are no negative real roots. So by Descartes' rule of signs, I either have 3 positive real zeros or 1 positive real zero. So if I go ahead and look at the graph of this thing, and it looks like there's a real zero very close to 1, so I'm going to just try and work this out and see. I'm just curious. So I'm going to bring down a 3. 3 times 1 is 3. 1 times negative 2 is negative 2. 1 times 4 is 4. So yeah, you see how when you synthetically divide something that's an actual root, you're going to get a 0 remainder, which means x minus 1 goes in evenly, so that's one of the factors. 1 is one of the zeros, and now what I'm left with is 3x squared minus 2x plus 4. And now I have a quadratic, so I could try and factor this thing, or I could use the quadratic formula and I could find all 3 of my zeros. So I'm just looking at this, and if I were going to try and factor this, I would do 3 times 4 is 12, and I need 2 things that multiply to equal 12 that add to negative 2. And I don't think there are any factors, so then I would probably do the quadratic formula, and we're going to do that in another unit. So I will have some other examples for you on finding zeros in class. Thanks for watching.